Changing the fuel of a giant ship sounds simple, but on a vessel nearly 400 meters long, fuel is not just something you burn, it is something you store, pump, heat, cool, seal, detect, isolate, and control. Because a cleaner fuel can still become a dangerous fuel if the ship is not redesigned around it. This is the hidden engineering behind the green fuel revolution. Not just how ships reduce emissions, but how they survive the new risks. A ship does not simply choose a fuel. It is designed around one. Fuel is not just something you burn. It dictates the tanks, the pipes, the ventilation systems, the engine control, and the required port infrastructure. Deep inside the hull of a modern cargo vessel, like the West Amelie, space is the ultimate currency. When engineers attempt to convert an existing ship to run on alternative fuels, they face an immediate bottleneck, the physical reality of the engine room. Maneuvering massive new components in and out of this highly confined area is a logistical nightmare. Every pipe, every valve, and every sensor must be perfectly mapped to comply with strict new safety approvals. The push for this massive effort comes from environmental regulations aiming for net zero emissions. But hitting that target requires completely rewriting the ship's internal layout. Furthermore, most alternative fuels have a lower energy density than traditional heavy fuel oil. If a new fuel requires double the volume to deliver enough energy for a long ocean voyage, it eats directly into the highly profitable cargo space. Changing a marine engine is not a simple mechanic's job. It is a heavy construction project performed inside a floating steel box, requiring specialized crews and massive structural alterations. You cannot just swap the fuel. You have to rebuild the ship's entire anatomy to safely contain it. But the ship itself is only half of the equation. Even when a breakthrough fuel is developed, like synthetic natural gas, which promises a climate-neutral footprint and zero particle emissions, the ship cannot simply pull into any port and fill up. The chemistry of the fuel might be perfect, and it might be entirely renewable, but it requires a totally new, highly reliable supply chain. If the infrastructure to move that fuel from an industrial chemical plant into a ship's bunker does not exist at scale, the vessel simply cannot sail. This is the ultimate bottleneck of maritime engineering. The entire global fuel network has to evolve at the exact same time as the vessels. To supply these newly designed ships, an entirely new class of vessel has to be built just to deliver the fuel. Enter the specialized bunker barge, designed to provide safer ship-to-ship fuel transfers. Constructing a vessel like this requires proven, robust containment technology, such as specialized membrane tanks built by extensively trained welders. Every inch of the stainless steel structure must be flawless, capable of withstanding extreme thermal shock and immense pressure. Before a single drop of actual fuel is loaded, The entire transfer system is subjected to rigorous cold tests. Freezing nitrogen is pumped into the pipes on the deck and through the auxiliary rooms, reaching all the way to the bunker mast. This ensures that every valve, every seal, and every component can function perfectly under extreme cryogenic conditions. The bunker mast itself is a first-of-a-kind engineering feat, designed to transfer fuel safely with enough flexibility to service a variety of megaship configurations. If a single component fails during this process, the alternative fuel never makes it to the cargo ships waiting in the harbor. When the fuel transfer finally happens out on the open water, the extreme physics of the process become visible to the naked eye. As cryogenic liquid flows through the connected flexible hoses, the sudden, extreme drop in temperature pulls moisture straight out of the sea air, instantly forming thick ice and dense fog across the entire piping system. This is not just a simple transfer of liquid. It is managing extreme thermal dynamics between two massive moving objects on the ocean. The fuel tank is not just storage. It is a critical piece of the ship's safety architecture. Cleaner fuel does not mean simpler fuel. Liquefied natural gas drastically cuts emissions, but it comes with a severe engineering catch. It must be stored at a cryogenic -162 degrees Celsius. LNG is the ultimate lesson in cryogenic complexity. At this extreme temperature, standard ship steel becomes dangerously brittle, and the fuel is constantly absorbing ambient heat, trying to boil off into a gas. To handle this, the ship's engineers are trained to remotely monitor optimum fuel temperature and tank pressure from the control room. Instead of venting the warming gas, modern systems capture this boil-off gas and feed it back into the propulsion system. It turns a massive thermal management problem into free energy, but it means the tank has to control temperature before the engine can control combustion. To burn this supercooled fuel, the engine itself becomes a highly complex piece of engineering. A modern dual-fuel engine like the MAN 35/44DF is designed to switch between heavy oil and gas on the fly without losing a single RPM of power. But natural gas does not ignite easily under simple compression like traditional marine diesel. To solve this, the engine injects a tiny, highly pressurized amount of liquid pilot fuel, functioning like a liquid spark plug, just to ignite the main gas mixture. Operating with injection pressures of up to 1,600 bars, this is controlled violence, managed by extremely precise software. This fuel-sharing capability allows the ship to adapt instantly, but it demands an entirely new level of mechanical sophistication inside the engine room. This cryogenic complexity extends far beyond the engine room. It dictates how the ship interacts with the port. Even during a routine truck-to-ship bunkering operation, specialized, heavily insulated piping must be used. As the liquid flows, the aggressive freezing and thick frost forming on the manifold serve as a stark visual reminder. You are transferring a supercooled liquid that will instantly expand 600 times its volume if it escapes into the atmosphere. To manage this risk during fuel transfer, traditional threaded pipe connections are no longer sufficient. Engineers now rely on dry cryogenic couplings. These specialized mechanical locks ensure that hoses can be connected and disconnected rapidly. But more importantly, they guarantee that not a single drop of cryogenic liquid hits the deck when the lines are separated. Supplying over 80 tons of LNG in just a few hours requires pushing massive volumes of extreme cold liquid through these narrow choke points. A leak here wouldn't just be an environmental issue. The extreme cold can make standard deck steel brittle enough to shatter. The coupling effectively isolates that hazard in seconds, ensuring that the fuel is transferred safely without exposing the crew or the vessel's structure. For much larger ship-to-ship or terminal operations, vessels utilize massive mechanical arms known as bunker masts. Before the LNG can even flow, these metallic arms must go through a strict pre-cooling process to prevent severe thermal shock to the piping system. Crucially, they are equipped with an advanced emergency disconnection system. If the receiving ship drifts too far from the pier due to unexpected wind or currents, the arm automatically cuts the flow, seals the valves, and physically breaks away. Before looking at methanol, we must deeply understand the fundamental spatial and engineering problem it solves. To do that, we have to look at the physical reality of LNG fuel gas tanks. The cryogenic tanks required to hold liquefied gas are absolutely gargantuan. Consider a single double-walled, vacuum-insulated tank designed to hold 770 cubic meters of LNG. Building these massive pressure vessels requires highly specialized welding techniques on 9% nickel steel to prevent brittle fractures. But the real engineering challenge is the cryogenic suspension system. These tanks must withstand the severe dynamic loads and potential collision forces of rough marine conditions. Because of their sheer size, these enormous steel structures cannot simply be squeezed into a finished ship. They must be lowered directly onto the hull while the vessel is still under construction in the dry dock. Once the upper deck is sealed, they are entombed forever. For ship owners, accommodating these immense tanks represents a massive sacrifice of highly profitable cargo space, trading sheer volume for environmental compliance. You can see this immense spatial sacrifice clearly during the manufacturing and assembly of an LNG-powered megaship, like the AI Denova. Weighing in at 184,000 tons with a staggering 20 decks and 2,500 cabins, this vessel is essentially a floating city, designed to accommodate up to 6,600 passengers. To power a machine of this colossal scale cleanly, engineers must allocate massive sections of the lower decks entirely to LNG storage and preparation. The installation of these gas tanks is a critical and highly complex phase in the dry dock. Around these gigantic cryogenic cylinders, engineers must weave thousands of sensors, double-walled piping systems, and complex ventilation shafts to ensure that any potential boil-off gas is safely contained or consumed by the engines. The sheer footprint of the fuel system is overwhelming, transforming the lower hull into a dense maze of cryogenic infrastructure. We see massive hull modules being lifted by giant gantry cranes at the shipyard, slowly piecing together a massive steel puzzle. The engine assembly alone requires precision engineering to ensure the dual fuel systems integrate perfectly with the power grid of the ship. Once the sections are moved into the dry dock for final integration, the true scale of the vessel becomes apparent. This floating marvel cost roughly 700 million euros to build, and a significant portion of that engineering effort went into accommodating the unique demands of liquefied natural gas. It is a stunning achievement in maritime heavy industry, but it highlighted a growing problem for global shipping. Space is a premium. Every cubic meter dedicated to a vacuum-insulated LNG tank, its tank connection space, and its protective barriers is a cubic meter that cannot be used for cargo, vehicles, or passengers. As environmental regulations tighten globally, the maritime industry realized that while LNG is a powerful transition fuel, its physical volume is a severe limiting factor. Ship designers began searching for an alternative, a fuel that could deliver drastic emission reductions without requiring the heavy, space-consuming burden of deep freezing cryogenic storage. They needed a fuel that was liquid at ambient ocean temperatures, a fuel that could utilize more traditional, flexible tank shapes built directly into the ship's existing structural voids. They needed a solution that would allow them to regain that lost architectural volume while still meeting strict international climate goals. That fuel is green methanol. The transition from a supercooled gas to a room temperature liquid seems like a straightforward upgrade, but in the world of mega ships, changing the state of the fuel completely changes the nature of the risk. While the tanks no longer need to survive -162 degrees, they must now contain a highly toxic, highly flammable chemical solvent. A green fuel is only useful if the safety system is faster than the failure. Methanol allows ships to regain that lost cargo space without sacrificing raw mechanical power. Heavy industries have successfully developed massive methanol dual-fuel marine engines capable of pushing out over 64,500 kilowatts of power, drastically cutting emissions while fitting within more traditional engine room dimensions. But while methanol removes the extreme cold storage problem, it is still highly toxic and highly flammable. The modular fuel supply systems that pump it from the bunkering station to the engine inlet are heavily fortified. They actively regulate flow rates and filter out impurities. The entire routing system requires complete automation and secondary double-walled containment barriers to ensure that a leak never reaches the open air of the engine room. Integrating this new safety architecture into a vessel requires thousands of extra engineering hours. The main engine is only one piece of the puzzle. The fuel supply system, the ventilation, and the safety protocols all have to communicate flawlessly. Because methanol is a low flashpoint fuel, and its flame can be nearly invisible in daylight, detecting leaks is paramount. Crews use ultrasonic technology to listen to the high-frequency hiss of a failing valve, finding invisible threats long before they trigger a catastrophic failure. The danger is not only whether the fuel burns, it is whether the ship can detect, contain, and isolate it. Ammonia is heavily researched for green shipping because its molecule contains absolutely zero carbon. But it is important to note that green ammonia is only truly green if the life cycle, the energy used to produce it, is also low carbon. From a combustion standpoint, it is incredibly stable and actually struggles to ignite, making it less of a fire hazard. But it has a terrifying bottleneck. Ammonia is deeply toxic. A heavy leak in an enclosed engine room is an immediate fatal hazard. To survive this fuel, the piping must be fully segregated, and ventilation systems must be massively oversized to instantly sweep away any accidental release before it reaches the crew. Because it resists ignition so stubbornly, forcing ammonia to burn efficiently inside a massive cylinder is a formidable mechanical challenge. Engineers spend years running experimental two-stroke test engines just to perfect the combustion timing. They must carefully balance the explosion to generate massive torque while strictly controlling the release of unburned ammonia and nitrous oxide, potent gases that could erase the environmental benefits of the fuel entirely. Delivering this toxic liquid to the engine requires heavy-duty armored infrastructure. Ammonia fuel supply systems are towering industrial skids that utilize massive pumps to push the liquid at up to 88 bar of pressure. Because ammonia is highly corrosive to standard materials like copper, the entire system must be fabricated from specialized stainless steel. The liquid is routed through reinforced double-walled piping equipped with continuous gas detection sensors. If a single drop of ammonia breaches the primary pipe, sensors trigger an automatic emergency shutdown, and the entire system is instantly purged with inert nitrogen gas. Transporting these massive supply skids into the shipyard and integrating them deep within the hull is a heavy lifting operation of its own. Ultimately, whether managing the cryogenic cold of LNG, the low flash point of methanol, or the extreme toxicity of ammonia, the crew must adopt a completely new operational mindset. The margin for human error has dropped to near zero, requiring constant, relentless vigilance. Changing fuel on a giant ship is less like changing a part and more like rewriting the ship's anatomy. We cannot simply wait 30 years to replace the entire global fleet with new builds. To decarbonize today, the industry has to retrofit. Retrofitting is often much harder than building new, simply because older ships were never designed around the physical and chemical realities of these new fuels. In some cases, like the Maersk Halifax, the entire vessel is physically cut in half in the dry dock to insert an entirely new hull section to hold methanol tanks without losing cargo capacity. A full dual-fuel conversion can take nearly 2 years of meticulous planning before the ship even enters the shipyard. It begins with comprehensive 3D laser scanning to figure out how to weave new, rigid cryogenic pipes through the congested layout of an old hull. Massive 9% nickel steel tanks and processing units are fabricated off-site. Meanwhile, deep in the engine room, the main engine is systematically dismantled. The cylinder heads, injection systems, and control electronics are entirely stripped and upgraded. A critical addition is the gas valve train, a heavily fortified unit that safely regulates and supplies gas to the engine at pressures reaching 300 bars. This unit acts as the ultimate cutoff switch in an emergency. The routing of the double-walled gas pipes must be perfect. The ship is effectively transformed into a highly complex floating gas plant. But simply changing the fuel system is not enough. Because these alternative fuels are expensive and often have lower energy density, maximizing propulsion efficiency becomes absolutely mandatory. Engineers completely overhaul the hydrodynamic profile of the ship. Outdated propellers are removed and replaced with newly cast, highly efficient blades designed specifically for the ship's new operating profile. Flow-optimizing rudder bulbs are welded on to reduce turbulent drag at the stern. Variable frequency drives and modern shaft alternators are installed so the ship can generate electrical power more efficiently while underway. Every piece of rotating metal, every underwater surface is relentlessly optimized to extract maximum forward thrust from every single drop of the new fuel. Upgrading the propulsion train requires removing the massive propeller shaft, remachining the bearings, and realigning the entire driveline to handle the new torque characteristics. This is where mechanical engineering meets fluid dynamics. Shaving off fractions of a percentage in drag to save thousands of tons of fuel over a ship's lifetime. However, heavy mechanics alone are no longer enough. The ship's digital brain must also be updated. Smart control systems are integrated to actively adjust the propeller pitch and engine RPM in real time. Digital monitoring on these modernized vessels is not just decorative. It is a critical part of the safety system, constantly countering resistance to squeeze out maximum efficiency. While retrofitting handles the existing fleet, the new builds demand engineering on a staggering scale. Building a modern dual-fuel engine from scratch focuses entirely on containment and control. These engines must withstand internal explosion pressures that would destroy a standard machine, while managing highly volatile gases safely. The focus is no longer just on heavy iron, but on the complex gas valve trains, double-walled fuel injection piping, and integrated nitrogen purging systems bolted directly to the cylinder blocks. Exhaust gas recirculation modules are strapped directly to the side of the engine block to scrub emissions before they can escape the funnel. Every component, from the fuel pumps to the massive turbochargers, is designed to balance brutal mechanical force with extreme environmental compliance. Assembling these giants requires specialized technicians working in pristine factory conditions, ensuring that every microscopic tolerance is met before the engine ever sees a drop of fuel. When fully assembled, a gigantic methanol-fueled engine weighs over 1,600 tons and stands as tall as a 4-story building. Lifting it into the hull of a new megaship requires the largest gantry cranes on Earth. This massive block of steel represents millions of dollars of capital investment, designed to safely push the largest moving objects on the planet while minimizing their carbon footprint. But whether it is a massive new build or a complex retrofit, the ship is only one part of the equation. A green megaship is utterly useless without a vast, reliable global network to feed it. The journey of these alternative fuels begins far from the harbor, deep underground, or in sprawling industrial chemical plants. Before a drop of fuel can ever reach a ship's tank, raw natural gas must be aggressively treated to remove impurities. Once purified, it enters a liquefaction train where heavy refrigerants are used to supercool the gas down to -162 degrees Celsius. At this exact thermal threshold, the invisible gas condenses into a clear liquid, shrinking its volume by an astonishing 600 times. This phase of the process is an industrial marvel in its own right, transforming a volatile atmospheric gas into a transportable, energy-dense liquid that can actually be loaded onto ocean-going vessels. It represents billions of dollars of capital investment just to create the starting line for the green shipping revolution. Without this initial purification and extreme deep freezing, the entire concept of operating a global fleet on clean liquefied gas would be physically impossible. Constructing the onshore infrastructure to produce and export this fuel is a megaproject of staggering proportions. Take the Ichthys LNG project, for example. Creating a facility capable of churning out millions of tons of liquefied gas annually requires assembling one of the largest continuous industrial sites on Earth. Because building such complex infrastructure in remote, harsh environments is deeply inefficient, engineers rely heavily on modular construction. Entire processing trains, towering pipe racks weighing up to 5,000 tons, and intricate electrical substations are prefabricated in specialized shipyards across Asia. Once complete, these colossal modules are loaded onto heavy transport vessels and sailed across the ocean to the construction site. Upon arrival, the heavy lifting truly begins. Fleets of self-propelled modular transporters, multi-wheeled robotic platforms, are driven underneath these massive steel structures. Slowly and methodically, they maneuver these colossal units off the docks and into place with millimeter precision. Thousands of workers, specialized welders and heavy-duty crane operators work in brutal heat to connect the modules, laying hundreds of kilometers of steel piping and thousands of kilometers of electrical cable. The sheer density of the engineering required to build just one of these liquefaction facilities is mind-boggling. It is an intricate web of thermal exchangers, high-pressure compressors, and massive gas turbines that all must function in perfect harmony. The logistical effort required to orchestrate this build rivals the complexity of a moon launch. Every single piece of steel, every specialized valve, and every kilometer of cryogenic insulation must arrive exactly on schedule. A delay in one module can cascade through the entire site, grinding the construction of the energy hub to a halt. When fully operational, this sprawling metallic metropolis will run 24 hours a day, 365 days a year. It operates as the beating heart of the global fuel supply chain, pushing thousands of cubic meters of processed energy out to the waiting tanker fleets. If this massive onshore machine stops working, the supply chain for the world's most advanced vessels comes to a grinding halt, leaving billions of dollars of shipping assets stranded at sea. The financial scale of such a project frequently exceeds tens of billions of dollars, requiring the combined capital of multinational energy consortiums. The site itself becomes a self-sustaining ecosystem, complete with its own massive power plants and water desalination facilities just to keep the industrial processes running. It is a testament to human engineering that we can build a machine of this scale to extract, freeze, and export the Earth's energy across oceans. At the end of these colossal liquefaction trains sit the massive storage tanks, capable of holding up to 150,000 cubic meters of liquid energy. Constructing these concrete and steel behemoths involves a stunning feat of engineering, raising the massive steel roof. Weighing over 1,500 tons, the entire roof structure is slowly elevated from the floor to the top of the tank, using nothing but low-pressure air blowers. Before any cryogenic fuel is ever allowed inside, these monumental tanks must prove their absolute structural integrity. They undergo extreme hydrostatic testing. Millions of liters of seawater are pumped into the massive containment vessels over several weeks. Engineers closely monitor the structures, ensuring that the foundations and the walls will not crack or buckle under the immense hydrostatic weight. These massive storage and export megaterminals dot the coastlines of major energy-producing nations. Endless arrays of fuel storage tanks stand as vital nodes in this new global energy network, waiting to pump their volatile cargo into the bellies of waiting megaships. As global demand surges, these facilities require relentless expansion. Terminals undergo massive upgrades, adding new loading arms, expanded breakwaters, and additional cryogenic storage capacity to handle the sheer volume of alternative fuel demanded by modern, environmentally compliant maritime fleets. This continuous expansion ensures that the maritime supply chain remains unbroken. Achieving operational status at these mega projects is a massive milestone. Sprawling complexes represent billions of dollars sunk into concrete foundations, heavy cryogenic piping, and fortified ship-loading berths. These sites are meticulously engineered to safely load supercooled gas onto vessels faster than ever before. Every successful test acts as a critical step toward creating a secure, highly reliable parking spot where the world's most advanced green ships can actually refuel safely. Terminals rely extensively on these floating assets to rapidly secure clean energy infrastructure. By utilizing an offshore FSRU, nations bypass the massive environmental footprint and decade-long delays of building a permanent land-based facility. The ship is securely berthed to a customized jetty, where high-pressure marine loading arms connect the vessel directly to the onshore pipeline network. It is a plug-and-play energy solution on a massive scale. The floating terminal must be capable of receiving fuel from inbound carriers while simultaneously regasifying and pumping energy to the shore. This dual operation requires complex fluid dynamics management and incredibly strict safety protocols. But the absolute pinnacle of this offshore infrastructure is the FLNG, the Floating Liquefied Natural Gas Facility, best exemplified by Shell's Prelude. The sheer ambition of building an FLNG is staggering. It is not merely a transport ship or a storage unit. It is an entire fully functional gas processing and liquefaction factory built onto a floating hull. During its assembly, shipbuilders constructed a hull nearly half a kilometer long, carefully lowering thousands of tons of processing modules onto its deck. Unlike a land-based plant, engineers had to solve the profound challenge of designing tall, heavy liquefaction towers that could safely process volatile gases while constantly pitching and rolling on the ocean waves. The internal tanks had to be designed to prevent the violent sloshing of cryogenic liquids from destabilizing the vessel. When an FLNG arrives at its permanent offshore home, it represents a paradigm shift for heavy industry. Weighing over 600,000 tons fully loaded, it extracts gas from deep beneath the ocean floor, processes it, and liquefies it right in the middle of the sea, completely eliminating the need for long subsea pipelines to the shore. To survive the extreme weather of the open ocean, including Category 5 cyclones, this colossal structure utilizes a revolutionary 93-meter-high turret mooring system integrated directly into its hull. This massive steel column is anchored to the seabed by chains so thick that a single link weighs a ton. The turret acts as a giant pivot point. As violent storms approach, the largest floating structure ever built acts like a weather vane, passively rotating around the mooring lines, constantly turning its bow into the wind and waves to minimize brutal structural stress. Deep-water energy projects represent one of the greatest engineering challenges in the modern world. To operate successfully in the harsh conditions of the deep ocean, companies must rely on advanced underwater technology, precise acoustic modeling, and highly specialized vessels. These massive floating structures are designed to extract valuable energy resources from locations thousands of meters below the sea surface. At such extreme depths, the environment becomes incredibly dangerous. Water pressure is immense, temperatures are close to freezing, and visibility is extremely limited. As a result, every piece of subsea equipment must be built to survive and function reliably for decades without failure. Engineers also face major difficulties in transporting, installing, and maintaining underwater systems. Specialized ships equipped with robotic arms and remote-operated vehicles are often required to perform complex tasks beneath the ocean. In addition, underwater acoustic technology plays a critical role in communication, navigation, and monitoring because radio waves cannot travel effectively through seawater. Despite these challenges, deep-water projects continue to grow because they provide access to valuable energy resources that are difficult to obtain on land. These achievements demonstrate how modern engineering can overcome some of the most extreme conditions on Earth. Bringing the best technology to these deep-water frontiers requires remotely operated vehicles. These deep-water robotics act as the eyes and hands of the engineers on the surface. They carefully connect massive subsea manifolds, install heavy wellheads, and route complex flexible pipelines in pitch-black water. Every connection they make must perfectly contain the intense pressure of raw gas surging upward from the Earth's crust to the floating processing facilities above. Maintaining this sprawling offshore infrastructure is a monumental task. World-class offshore shipyards deliver the necessary heavy maintenance. They fabricate replacement parts, service the heavy transport vessels, and ensure that these vital offshore assets and deepwater fleets remain in flawless operational condition year after year, safeguarding the continuous flow of the global energy supply chain. Once the fuel is processed, either on land or at sea, it must be transported. Megaships are designed specifically for this task. As they arrive at receiving terminals, these vessels carry hundreds of thousands of cubic meters of liquid energy. They are the mobile pipelines of the ocean, moving volatile cargo across the globe. Operating fleets like this demonstrates what it truly means to deliver liquefied gas. These vessels are powered by redundant twin engines and twin propellers for maximum reliability, ensuring they never lose power while carrying such a dangerous payload. But getting the volatile fuel out of these transport giants and transferring it into the cargo ships that actually need to burn it is where the highest operational risks are concentrated. Ship-to-ship bunkering is one of the most concentrated points of risk in the entire global supply chain. It is a high-wire act of fluid dynamics and heavy machinery. Performing this transfer while underway, where both vessels are constantly moving, demands flawless synchronized coordination. When two massive ships maneuver alongside each other, immense hydrodynamic forces pull and push their hulls unpredictably. In extreme environments, like the freezing darkness and ice-choked waters of the Arctic Circle, this operation becomes intensely dangerous. During an STS operation in these conditions, the crews must contend with violent winds, sub-zero temperatures, and the constant threat of sea ice pushing the vessels apart. A single mistake in steering or speed adjustment can cause thousands of tons of steel to collide. The mooring lines are under immense tension, holding the ships tightly together while the cryogenic fuel is pumped across the gap. It is a grueling, high-stakes ballet performed in some of the most unforgiving environments on the planet. The engineers overseeing the transfer must constantly monitor the load on the winches and the tension on the specialized hoses, knowing that any sudden movement caused by a rogue wave could trigger an immediate emergency shutdown. The margin for error is effectively zero. To mitigate this kinetic energy, Expert crews deploy giant pneumatic Yokohama fenders between the hulls, acting as massive shock absorbers. Once the vessels are securely lashed together, heavy-duty flexible cryogenic hoses are carefully lifted by deck cranes and bolted directly to the receiving ship's manifolds. The complex manifold systems dictate exactly how fast and at what pressure the extreme cold liquid can be forced into the receiving tanks without causing a catastrophic pressure spike. During these ship-to-ship bunkering operations for marine customers, liquid is pumped at incredible rates. Through all of this immense transfer of energy, the most critical safety component is the emergency release system. It constantly monitors the physical distance between the ships. If the ships begin to unexpectedly drift apart, the system does not wait for human intervention. The guillotine valves trigger in milliseconds, slamming shut and cleanly severing the physical connection to prevent the hoses from rupturing. At the core of this immense and highly automated maritime system lies the most critical component, the human element. Operating an advanced LNG carrier is not a routine task. It demands a level of expertise reserved for highly trained maritime professionals. While the vessel's engine powers its movement, it is the crew that ensures its safety under all conditions. On the bridge, the captain and deck officers carry an extraordinary responsibility. They must guide a massive ship through narrow, congested waterways where even a minor miscalculation can have serious consequences. Every decision, whether adjusting speed, altering course, or responding to changing traffic patterns, must be executed with precision and confidence. These vessels, often described as floating bombs due to their cargo, leave no room for error. Handling such enormous mass and inertia is not instinctive. It is learned through years of rigorous training and simulation. Officers spend countless hours in advanced simulators, practicing emergency scenarios, complex maneuvers, and navigation in extreme conditions. This preparation builds the judgment and composure required to act decisively in real-world situations. Beyond technical skill, working at sea also demands discipline, teamwork, and constant vigilance. The crew must monitor systems around the clock, anticipate risks before they arise, and maintain strict safety protocols at all times. In the end, no matter how advanced the technology becomes, it is human expertise that stands as the vessel's final line of defense, ensuring that every journey is completed safely. Life on board a floating LNG facility or a megaship is dominated by technology. Deep below the deck, the engineering crew lives in a world of complex data. Staring at vast banks of monitors in the central control room, they meticulously track the exact temperature, pressure, and flow rate of volatile fuels pulsing through the ship's veins. On these advanced vessels, emergency response protocols are not bureaucratic formalities. They are rigorous survival training. Every single crew member must know exactly how to isolate a leak or seal a compromised bulkhead in total darkness. Companies dedicated to maritime excellence strive to maintain this extreme standard, emphasizing safety, passion, and integrity as their core values. They live on these floating pipelines for months at a time, crossing harsh oceans separated from their families. Ultimately, these men and women are the final, most important barrier between a highly engineered machine and the unpredictable, unforgiving forces of nature.